Flomatic is very pleased to make this short presentation on our automatic control valve program, which is NSF ANSI 61 certified and also qualified under the American Iron and Steel Act, the AIS. Short 15-slide presentation will explain how does an automatic control valve work and what are the component parts. Flomatic automatic control valve, it's very simple, reliable construction. It contains very few parts. Number one, top cap, spring, diaphragm plate, diaphragm, lower diaphragm plate, spool piece, rubber valve seal, valve stem, valve seat, and a fusion epoxy valve body that meets NSF epoxy requirement. The main components of the valve, it's an inlet portion and an outlet portion, a top cap or power chamber, and the diaphragm that separates the top cap from the main valve body, and a spool piece that moves up and down, and then you have a stainless steel seat and the main valve body. Here is an explanation on how the valve's power chamber works, open and closing the valve. Now, in fully open position, the spool piece moves all the way up, and there is no pressure in the power chamber. See the red arrow. When the valve goes closed and there is no flow through the valve, the power chamber is pressurized and the spool piece moves down and seals off the flow. Hydraulic principle of operation. Scenario 1. With the cover chamber vented to the atmosphere of the valve will open from the line pressure. The flow direction coming in from the left through the valve to the right, and the power chamber showed the red color has no pressure as it is vented to the atmosphere. The spool piece moves all the way up. Scenario number 2, if the inlet pressure is connected to the top power chamber, the valve will go closed. If we connect the inlet to the upstream pressure connected to the power chamber, if the line pressure is 100 psi, the power chamber will also see 100 psi, and the valve will go closed, and there will be no flow. The reason for this is that the diaphragm area is much larger than the valve seat or orifice. So you have a hydraulic advantage. Let's explain the hydraulic advantages in scenario 2. If inlet pressure is connected into the cover chamber, the valve closes tightly. In this example of the 6-inch size control valve, for instance, it's the diaphragm area in a 6-inch valve, which is approximately 11 3/4 inch in diameter, the surface area is 108 square inches. On the other hand, the seat surface area on a 6-inch control valve is 28 square inches. If the inlet pressure is 100 psi, we will multiply the pressure, psi, times the surface area in square inches and get the force in pound. The closing force, 100 psi on the diaphragm area of 108 square inches, gives us a closing force of 10,800 pounds. Opening force on the seat area is 100 psi times the valve seat area, 28 square inches, gives us only 2,800 pounds of force. The difference is 8,000 pounds of the very convincing closing force of the valve. Scenario 2, we explained the hydraulic relationship that makes the valve fully open or fully closed. In scenario 3, we'll explore this relationship to a higher level as follows. If a small pressure reducing valve is connected to the power chamber, in this case, a pressure regulating pilot, we have a high unregulated flow upstream and want to regulate it to a lower constant downstream flow. Knowing the hydraulic relationship, we install the pilot valve, a pressure regulating valve, connected from the top power chamber of the valve to the outlet downstream. The pilot valve is adjusted, in our case, to 50 psi, while the inlet could be fluctuating, let's say, between 90 to 125 psi. To make this control valve work properly, we need a flow restrictor, an orifice valve on the inlet. Why? The inlet or upstream pressure is higher than the valve's outlet pressure, causing the valve water flow into the power chamber faster than the pilot valve's ability to take water out. And to regulate the valve and modulate to a constant downstream pressure. In earlier slides, we explained the hydraulic advantage, the larger diaphragm diameter versus the diameter of the orifice. In most hydraulic control valves, the ratio is about 1:3. However, the pilot valve has a much greater ratio to diaphragm and orifice, as the valve incorporates a very small orifice area, giving us a ratio about 1 to 68, which makes that control valve overall operate at a much more convincing regulation than the main valve. And that's why the main valve is referred to as the slave, and the pressure reducing pilot as the pilot, giving the regulation accuracy to the automatic control valve. As we can determine from previous slide, the pilot is very important in making the main control valve body operate. Pilot controls can be hydraulic, electronic, solenoid, battery operated, or a combination of both hydraulic and electronic. Each manufacturer's products have unique characteristics and highly individualized installation, maintenance, operation instructions that dictate the care and operation of the pilot control systems. There are many types of pilot control system for diaphragm actuated valves, including but not limited. Perhaps the most common is the pressure reducing control valve, pressure relief valve, combination of pressure reducing, sustaining, etc., rate of flow, altitude, and remote sensing pilots. Scenario 4. Other types of pilot valves that can be connected to the control valves includes pressure reducing pilot, or PRP, flow control pilot, FCP, back pressure pilot, or a BPP, pressure differential pilot, PDP, accelerator pilots, ACP, solenoid valves, 2 or 3 or 4th weight, modulating control valve pilots, AMP, or non-modulating, ANP, modulating float control valves, FMP, and finally non-modulating float pilot, FNP. We have discussed in detail the operation of the control valve, the various pilots. Here are some of the most common automatic control valve configuration. The basic valve we call C000, model C101, probably the most common valve, which is the pressure reducing valve. Altitude valve, model C201, or the non-modulating model C205. Another popular control valve is the back pressure valve, model C301, followed by the pressure relief valve, also very common valve, model C401. Surge arrestor to eliminate water hammer in long pipeline, model C501. Then we have pump control valve, model C01, or dual chamber 621. Float control valves modulating, model 701, and non-modulating, model 705. Solenoid valve, model C801. Flow control valve, model C901. And finally, the hydraulic jack, model C001. In addition to the 10 most common automatic control valve configuration, there are many additional combination under each product family. For instance, the series C100 pressure reducing control valve has additional features of dual pilots for additional flow and speed. Another very popular combination is our C103, pressure reducing with external check, often used for booster pump systems. Back pressure combination with a pressure reducing valve are common used with pump systems, line shaft turbines, to ensure that a well, for instance, or a tank is not pumped empty. And the back pressure feature ensures that the pump does not overdraft the supply. And also pressure reducing with a normally open or normally closed electric solenoid. And in addition to these combination, we have similar combination for the Series 200 altitude valves, the Series 300 back pressure, the Series 400 pressure relief valve, the Series 500 surge arrestor, Series 600 pump control valve, the Series 700 float valve, Series 800 solenoid valve, and the Series 900 flow control valve, in addition to the Series 1000 hydraulic check. As you can see, there is almost an unlimited combination of pilot controls for the hydraulic control valves. You will find more on Flomatic webpage, www.flomatic.com. On behalf of Flomatic Corporation, thank you very much for watching this slide show on our automatic control valve. Please let us know if we can help you specifying a valve for your application. Thank you very much.